Okay, so welcome back everyone to the last session of the day. So Mithat Unsal will be giving the third lecture of this series. So Mithat, over to you.
Okay, thank you very much. So this lecture is about gauge theories, and in particular Yang-Mills theory in 4D. Okay, let me write this down. 4D Yang-Mills theory and some other gauge theories. And I will present various things. This notion of adiabatic continuity, I will define what it is. I will describe its connection to large and volume independence. This is also called Eguchi-Kawai reduction, which is a very useful numerical technique. And I will describe, how to do semi-classics, reliable semi-classics, and tell you some things about, if time permits, some things about IR-Renormalons and some types of pions. Okay. So Yang-Mills theory is this property called asymptotic freedom. At high energies, this is energy in some sense. At high energies, the coupling constant becomes small, but as you go to lower and lower energies, it gets larger and larger. So here there is experimental data. There is also theoretical description curve. So long distance is strongly coupled. So the standard tool is to use lattice, and analytical methods are much harder because of the strong coupling. A question you can ask yourself is following. Actually, I will go a bit slower this lecture. So feel free to stop, and I will go more conceptual for a time. But let me tell you the question. The question is, can we find a regime of asymptotically free theories which become strongly coupled at long distances, where these gauge, in these theories, the non-perturbative dynamics become calculable? Can we find a regime such that? On R4, this is not possible, okay? And we are interested in theories like Yang-Mills theory or QCD. Of course, this is a very desirable thing to have a reliable semi-classical calculation in these theories. But an obvious question is whether this is possible or not. At least on R4, it is not known if such a framework exists. And as I said, as you go to long distances, the theory necessarily becomes strongly coupled. And in this context, at least for Yang-Mills or n=1 super Yang-Mills, just making it purely supersymmetric, the supersymmetry does not help either, because supersymmetric theory also becomes strongly coupled. n=2 is special. n=2 is Seiberg-Witten theory, but it also has, in this thing, there are techniques that works on R4, but it's also special in the sense that it has some elementary scalars in it. Scalars. But the distinguishing feature of these theories, Yang-Mills and QCD, is the fact that there are no elementary scalars in the theory. So at least in the context of theories without elementary scalars, on R4, this is not possible. Now, we can consider these theories on different form manifolds. For example, something like R3 cross S1. and study their dynamics as a function of radius. However, this is something well known, at least in the standard form. And if you go to small radius, the theory indeed becomes weakly coupled because of the asymptotic freedom at the scale of the radius. But the theory is non-analytic as a function of radius. So there is a phase transition, and as you want to go from strong circle to large circle, there is a phase transition on the way. So it's not desirable. And here in the standard studies, S1 is a thermal circle where beta is 1 over temperature, at least in the standard compactification. And as I say, despite the fact that the theory becomes, some aspects of the theory becomes weakly coupled here. I'm not saying quark gluon plasma is weakly coupled or long distance theory is weakly coupled. Some aspects of the theory becomes weakly coupled here. It doesn't help because of this singularity in thermodynamic observables. For example, if you look to free energies or things like that, there is a singularity in these quantities. Okay. So this is what happens thermally. Thermally, there is a phase transition or some rapid crossover around the strong scale. This beta critical here is around the strong length scale of the theory. And the idea of adiabatic continuity wants this weak coupling regime, to be smoothly connected to strong coupling regime. If this is possible, then we can do some analytic computation in this regime and learn something quantitative as well as qualitative about non-perturbative problems such as, for example, confinement, chiral symmetry breaking, or multi-branch structure of vacua, or other things like mass gap and stuff like that. Okay. Let me now tell you this notion of adiabatic, okay, it goes too fast, this adiabatic continuity. This is actually related to something well known in lattice field theory, but it is it was something difficult to achieve. You can think of it as a spin-off of this nice idea of Eguchi and Kawai, which is called large N reduction or volume independence, or Eguchi-Kawai reduction. What Eguchi-Kawai says is that is far more stronger than continuity. They really imply volume independence. This is the reason that it's sometimes called large N volume independence. This is the fact that observables become, if some conditions are satisfied, observables become independent of compactification radius. This is something very interesting because it tells you that you can reduce, R4, you can compactify it on T4 and make it reduce to a tiny T4, to a point, and you can preserve some of the properties on R4 even at the point, so you can reduce it to a matrix model where, this is in some sense in matrix model, this is zero dimensional. But it also tells you that, at large N, there is something interesting going on, and you can write down space-time degrees of freedom in terms of matrix degrees of freedom. So let me first tell you what Eguchi-Kawai says, or what is large N volume independence rigorously, more precisely. It says that you can start, for example, with some SU engaged theory on R4 and consider its various toroidal compactification. either R3 times S1, R2 times T2, or all the way to T4. And the idea tells us that there is no volume dependence in leading large n behavior of topologically trivial single trace observables. These are Wilson loops, as well as a connected correlator of Wilson loops. Physically, for example, string tensions, mass gap, and stuff like that, there is no volume dependence, provided there are no phase transition as the volume is shrunk. So that means there is no spontaneous breaking of a symmetry called center symmetry or translational invariance. There is a standard proof of this argument by using, lattice field theory. You can use large N loop equations. This is what Eguchi-Kawai did. And you can also use N equal infinity classical dynamics. This is what a method developed by Larry Yaffe. Well, the only problem with this, probably the biggest problem with this idea is that this part provided. So because it's very hard to find any theory or any construction in which the absence of phase transition can be shown, because but on the other hand, the idea is very attractive because you can take a theory on R4 and reduce it to a point, and it may be cheaper to simulate a lattice with just one side than lattice where you have, large volumes. So because of this attractiveness of this idea, quite a bit of effort have been devoted to it in the early and mid 80s. There are some very nice works, but almost always there was a phase transition. So at least in Eguchi-Kawai, twisted Eguchi-Kawai, later on it's shown not to work, but quenched Eguchi-Kawai. Twisted Eguchi-Kawai is actually a construction which is relatively beyond its time, because it is extremely interesting and theoretically intriguing. This is the construction of Gonzalez, Arroyo, and Okawa. First, it was thought that it works. Around 2010, there were some reports which were saying that it failed, but then it revives again. It still works. This twist Eguchi-Kawai works. But technically speaking, if you ask technical question, why this volume independence fails or works, so the order parameter, if you do, for example, R3 times S1 compactification, I come to this in a moment. The order parameter is the Wilson line. This is an order parameter used to determine the phase of the theory. And if you look to calculations in the past, this order parameter always gives a negative sign and instability. And ultimately, many people gave up. And what we want for the either volume independence or adiabatic continuity, we want a positive mass for the order parameter. So we don't want the symmetry to be broken, okay? But this seems to be impossible, because if you do standard, for example, R3 cross S1, it is impossible. If this is temperature, if you heat up things to sufficiently high temperature, if you start with the hadronic phase, which is the phase that we live in, and if you heat it up enough, it will go to another phase, quark-gluon plasma phase. So it seems impossible to achieve this. Now, let me make the discussion on R3 cross S1 more precise, because later on I will use it to also build semi-classics. So this theory, Yang-Mills theory on R4, has a one-form symmetry. It is a Zn one-form symmetry. It acts on the Wilson lines. When you, this is on 4D. When you compactify the theory on R3 cross S1, this Zn one-form symmetry becomes still Zn one-form symmetry on 3D, and Zn zero-form symmetry again on 3D. And this part of the symmetry is the thing that acts on the Polyakov loops. So on R3 cross S1, you can write down these Polyakov loops. I call them omega, which is exponential I A gauge field, let's say in the compactified direction. So this part acts on the Polyakov loop. Polyakov loop transforms under this zero form part of the center symmetry. And hence, this means that trace omega is the order parameter. So if you are, let's say this is L, if you are L critical, if you are L larger than L critical, you are in this phase. And if you are L lesser than L critical, here you are in this phase, okay? So there is a standard phase transition here, and it tells you that this idea of Eguchi-Kawai, at least if you apply it on R3 cross S1, it is impossible to achieve, at least in this format. And technically, the reason that it fails is that if you do a one-loop calculation for this holonomy, gauge holonomy, this is something done in 1981 by these gentlemen, Gross, Pisarsky, and Yaffe, that you obtain a potential, but the sign in front of the potential is minus. So all of these order parameters are tachyonic. The students may or may not be familiar with this potential, but they are certainly familiar with the results of this potential. If you calculate this potential at its minimum, the minimum is at omega equal 1, for example, where omega is an n by n matrix. That means all n eigenvalues clump, you know. If you calculate this potential at the minimum, you will obtain these Stefan Boltzmann laws for n squared minus 1 gluons. So this is the free energy for the gluons. So, or the appropriate pressure for the gluons. It's like black body radiation. Pressure is minus free energy. So with some pressure dictated by gluon gas. Okay. So at high temperature Yang-Mills, this is inevitable. So there is no room for negotiation. If you go to high temperature, this is what will happen on the circle compactification. And this is also true for any QCD-like theory. And there seems to be no hope here to achieve neither volume independence nor adiabatic continuity. But there are ways to go around it, okay? So when I was just after graduate school, I realized that the counterpart of this calculation in supersymmetric theories gave 0. Here, when you consider this calculation, you are always considering usual partition function for the system, trace over the Boltzmann factor exponential minus beta h. And considering this thing in the PET integral formulation preferentially. But I realized that the counterpart of this calculation in supersymmetric gauge theory.
I have a question.
Go ahead.
Thank you. The question is the following, that you are working with R3 cross S1.
Yes.
Now, yes, so at finite temperature, now suppose I work at 0 temperature, so I just work at R4, then, as you know very well, actually, that we can really map the Eguchi-Kawai or the modified Eguchi-Kawai model reproduces the leading order perturbation theory of Yang-Mills theory, right? And this was shown by Gross and Kitazawa and Shumik Das and myself long time ago. So there the idea was that it's the translation group of the gauge theory that is coded in U infinity. And
of course,
I think that theory is completely fine. That part of Eguchi-Kawai reduction slightly modified by these.
twisted Eguchi-Kawai, as I said, it is fine.
Yeah,
it works.
It's the finite temperature that spoils the works, according to you.
Twisted. I will come to finite temperature. I will actually rescue R3 cross S1 as well in a moment. Okay. But at least the traditional form of the twisted Eguchi-Kawai also failed in 2010. But then Gonzalez Arroyo and Okawa constructed different twists, different set of twists.
Yes.
And they have shown that you can make it work again. So there was some gap between these two. But I will make it work for any, I will make it work in a moment on R3 cross S1, R2 times T2, etc., etc.
Nice.
Okay. In a moment, I will show that all of these others are also possible.
Okay. Thank you.
So sure, on R3 cross S1, so if you use standard trace, a standard partition function, it will never work. But in supersymmetric theory, if you look to what people do when they do compactification, they calculate a Z2 graded partition function. And in supersymmetric theory, this is just an index. But if you consider this thing in QCD with adjoint fermions, which is with NF greater than 1, this is the number of Weil or Majorana adjoint fermions, this theory is non-supersymmetric. And I will show you that volume independence will work in these theories, even on R3 cross S1. Now, so what happens in the supersymmetric theory? It is important to understand practically why, this tachyonic instability did not arise in supersymmetric theory. First of all, it's important to appreciate that because of this -1 to the F, fermion boundary condition is periodic, not anti-periodic. So this is the insertion of -1 to F. And in the Hilbert space formulation, you are not doing a sum over bosonic Hilbert space plus fermionic Hilbert space. This would be usual partition function. This Z tilde is bosonic Hilbert space minus fermionic Hilbert space, because this -1 to F is telling you that for states which are fermionic, insert an overall minus sign, okay? So, and this is the difference. And if you look at practicality, that -1, you get modified by a +1 because of the adjoint fermion. And you get -1 + 1, 0. So the coefficient here, the coefficient of the Wilson line becomes 0. And immediately you can deduce that if you put NF greater than 1, if you put adjoint fermions, okay, multiple adjoint fermions, well, adjoint, then you can make the prefactor positive and you can obtain this result. Okay, this is quite important results. The coefficient is positive for NF greater than 1. And however, you no longer have a thermal interpretation, and And on the other hand, it tells you that you can make the idea of volume independence work, as well as it will also provide some interesting semi-classical regime that I will come back to you. This is one of the most interesting sign flips that I know, So this kind of calculation between 82 and 207 always had a negative sign in front. And this tells you that you can make it into some positive sign and make these order parameters non-tachyonic. Is that clear?
Yes,
Okay.
yes. Beautiful.
Okay. Okay. So it's relatively nice and simple. So what happens then? Okay, so so far I described something with large n, but this calculation is actually also valid at finite n. It tells you something very interesting, even at finite n. If you go to...
I have a question.
Sure.
So the meaning of beta in this expression is the extent in each direction, or
let's call L. It is not thermal anymore. Okay.
okay.
So it is R3 times S1 L. You have to interpret this. Let me write this down. Okay, let me take this thing to my hand. I can write more comfortably. You have to interpret this as a non-thermal compactification. So it is, if you wish, it is zero temperature. If you were to go to Minkowski, this corresponds to R2, 1 cross S1L. This is really compactification of a spatial direction. So the temperature is always zero. You just compactify the spatial direction. Whenever you compactify, you are free to choose any boundary condition allowed by symmetries. So the time direction in the Minkowski setup is still here. And if you continue this to Euclidean setup, R3 times S1L, this is zero temperature, but one of the circle is a non-thermal circle. Okay, is that good?
Yes.
Okay. Now what happens? Okay, so then we have these trace omegas. The minimum of this potential, the coefficients are all positive definite. So minimum of this potential is that trace omega is zero, trace omega square is zero, trace omega cube is zero. All the way, all of these things are protected by symmetries. The only thing, all the way to trace omega n is zero, then trace n minus 1 is zero. Omega n can be non-zero, but this doesn't conflict with the Zn zero form symmetry. This thing is now safe. It is protected. Okay. Now, what happens if you omega is an n by n matrix with eigenvalues I theta 1, I theta n? If you make all of these things zero, if you make them zero, then you are pushing the eigenvalues of omega from each other. You are pushing them away from each other. So it is very important. Now, I am now considering finite n. Okay, finite n. Now, in the usual case, thermal case, this is the thermal case, all the eigenvalues clump, and you do get usual Kaluza-Klein decomposition. Modes are separated from each other in the Kaluza-Klein. These are Matsubara frequencies in units of 2 pi over L. But in this case, the eigenvalues repel each other. Okay, so if you look to the perturbative spectrum, there are, in some sense, you can say that when the eigenvalues repel, I will say this one page later, SUN reduces down to U1 to n-1 abelianized at long distances. So this is in some sense similar to Polyakov model, but there is a fundamental difference here. Holonomy is your scalar field, and it is compact, and this makes a huge difference compared to Polyakov model. And you can see that there are actually W bosons here. W bosons have masses like 2 pi over Ln. So you immediately see that the spectrum here, this is related to the question, to the remark that was made about twisted Eguchi-Kawai and how for example, Gross-Kitazawa showed the emergence of the beta function from the matrix model. If you take, for example, the spacing between these W's, they are 2 pi over Ln. Even if L is fixed, if you take n to infinity, you get a continuum here in the center symmetric background. So this continuum is like continuous momentum modes, continuous momentum modes on R4. Okay, so it is as if there is no distinction between the theory of, perturbatively, there remains no distinction between the theory on R3 cross S1 and an R4. The momentum to get encoded to this eigenvalue, to this, you get this much finer spacing of the modes. And so, okay. And you can actually calculate beta function at arbitrarily small s1 here, or like Gross and Kitazawa did in the matrix model, and you will get your 11/3 and beta function coefficient without any problem. But this thing, this setup here at finite n provides a setup in which you get control over semi-classical dynamics, control over semi-classics. And I will describe from here on what happens. And you can address questions like mass gap, theta dependence, multi-branch structure, confinement, and things like that, okay? I will skip these pages, okay. And I also described, let me emphasize, you see the adjoint again in the thermal partition function. This is the quantity that we are calculating. If you are doing this twisted partition function, as I said in supersymmetric theory, this is the supersymmetric index. And for SUN theory, for example, this thing Z tilde L for SUN gauge theory, it is just n. It is indeed independent of L. It's counting number of supersymmetric vacua. And indeed, you can show that there are n supersymmetric vacua analytically on small R3 cross S1. And because of this L independence, this also goes to R4. Okay, this is number of vacua in supersymmetric theory. Okay. Now, however, you can see that this whole construction relies heavily on the existence of the adjoint fermions. And you would like to have this thing also work in, some idea like this also work in Yang-Mills theory. One thing you can do is you can make these adjoint fermions massive, and you can increase the mass. And ultimately, of course, when they decouple, you know, the center will break. But this gives us a related idea, and this was an idea I came up with Larry Yaffe in 2008. We considered Yang-Mills theory, and we considered some pure Yang-Mills now I am talking about, and I will make this idea work in pure Yang-Mills as well. One can consider a double trace deformation of the pure Yang-Mills theory. This is a very special deformation because deformation is trace omega and trace omega dagger and this kind of double trace operator. And with this double trace, you can actually, did I put a plot here? No. Let's say this is your deformation parameter. This is R4. Normally on R3 cross S1, you have this phase transition. Okay, this is R3 times S1. And if you increase this deformation parameter large enough, you can go here when it's sufficiently large deformation parameter. And this theory on R4 will be adiabatically connected to theory on R3 cross small s1 here. And you can actually show something very interesting. First of all, okay, this deformation action is order n square, and this deformation is also order n. Because of the double trace nature, it does something very interesting. So it is not a small perturbation in the sense of large n counting. So you can show that this double trace deformation does not alter things like or string tensions. And this is related to this special feature of being double trace and each trace being charged under center. Now, this deformation is order n square. It does stabilize the symmetry, but its effect on the dynamics is suppressed by 1 over n factors. Okay, how is this possible? You change the phase, but then you remain. The mass gap you calculate here in the large n limit is same as mass gap there. For example,
can I ask a question?
Sure.
So regarding this deformation term that you are adding to the action, what is the intuition behind picking this particular deformation?
Is not enough because are you going to
Hello, Mithat, we cannot hear you.
Oh, I'm sorry. I put my hand to the microphone, I think. Okay. So
Okay.
part of the intuition is coming from here, and other parts I will tell you where the intuition is coming from. It is coming from lattice gauge theory again. Okay. So I will tell you something about something very peculiar about this deformation that somehow I knew, I guessed at the time. Okay, but let me tell you what it does. Okay.
Okay.
So you know you can write loop equations. These are Migdal-Makinko equations in let's Yang-Mills theory. You know, these are in effect Migdal-Makinko or some more version of the Schwinger-Dyson equation for Wilson loops. I think these are, I didn't put here the reference. I think for the first time they are written properly and correctly by Wadia, who may be there, I think. And very nice paper.
Thank you. Thank you. I'm here.
Oh, of course. Yeah.
Thank you. Thank you.
The original had some problems and it is written completely correctly in this reference here. And okay, and the idea is following. So for the original Yang-Mills theory, a Wilson loop turns out to be this lattice parameter divided by NC, some you know, some small placket deformation of this loop in this format. Let me show you, okay, what happens when you add this extra term, okay? When you add this extra term, what happens is that something is, okay. This extra term is variation of this double trace omega K trace omega dagger K kind of thing. And there is also variation of the original loop. What happens is that one of these Wilson loop, let's say this is your C, okay, attaches to that C at some point and makes something like that. And the other one is like spectator. This goes like this at this point, and this goes like that. But now, once you stabilize the center symmetry, okay, once you stabilize that center symmetry, you can use factorization. But after factorization, this is the effect of the extra term, okay, double trace term. After factorization, each one of these things is charged under center symmetry. So each one of these things is 0. So you show that, and the effect of the double trace is order 1 over n square. So this deformation guarantees center stability. Hence, it ensures this large n factorization. And each factorized piece, you know, there are these two pieces. And now factorization tells you can write it like that. Each factorized piece is charged under Zn0 form center symmetry. And since you guaranteed center stability, this is 0, this is 0. The only contribution here is order 1 over n square, okay? So the effect of these, you know, of this deformation, which is not a perturbation in the sense of large n, is 1 over n square. I think this is quite remarkable that you do this deformation and the effect of this delta S deformation is order n square on the observables. So this is an insightful comment by Veneziano. He said, you know, when I explained this to him in around 2009, he said, it's like a good Samaritan. It does the good deeds and you do not even know it existed. So, but it is also a bit counterintuitive. Okay. So this is the story now, the summary of the large n story. So normally in ordinary Yang-Mills on R3 cross S1, we would go to this deconfined regime, and it is not related to the confined regime. It is not analytically connected, but with deformed Yang-Mills, we can achieve this volume independence. And never mind, oh, this is deformation equivalence. Oh, yeah, these are some words. It's not important, but you can connect this theory on small circle to R4, okay? Actually, yeah, this is the deformation parameter I explained. Interestingly, you know, there is also an old paper, relatively quite unknown paper by Joe Polchinski, who actually, without constructing this explicitly, he says that this is high temperature limit of the confining phase. It's really not temperature, but he talks about analytic continuation of the confined phase to high temperature. It is a related idea, but this could have been made much sharp, but people, I think, did not appreciate much at the time. Now, let me tell you about the dynamics of these deformed Yang-Mills theory. I can also tell you QCD adjoint, it doesn't matter. QCD adjoint is different in some senses because of the existence of fermionic zero modes. I told you that SUN dynamics abelianize at long distances to maximal abelian group. This is similar to Polyakov model as well as Seiberg-Witten theory. If you look to what the coupling does, it starts to grow. If it was on R4, it would continue to grow. But because of this abelianization, these W bosons decouple, and there is nothing to flow in the loops. And the coupling constant really becomes small and a constant, okay? So you obtain this theory and you have this U1 to n-1 theory, you have U1 to n-1 photons. Since 3D long distance theory is 3D, but importantly, the short distance theory is 4D. And because of that, all of the standard ABJ anomalies are there, and they have very powerful implication, as well as the index theorem, Atiyah, Padotti, Singer, as well as index theorem for Dirac operator on R3 cross S1 on monopoles is operative. These are there. So many features of the theory are dictated by its 4D behavior. Okay, it's really 4D, but long distance description is 3D. Okay, so in 3D you can always dualize the photons to two scalars. So if it is n-1, then this is n-1 component. This dual photon is an n-1 component, because a photon has one polarization in 3D, and the scalar also has one polarization. It has 1 degree of freedom in 3D. And these photons remain massless to all orders in perturbation theory. The question is what happens non-perturbatively. But similar to the Cyber-Clifton as well as Polyakov, well, more similar to Polyakov, whenever you have this, you have monopoles in the game. These monopoles on R3 cross S1, these are actually fractional instantons. Okay, let me see where I said something about them. Okay, let me do this page first, then I will go back. So there are actually, with SUN broken down to U1 to n-1, there are, normally you would think that there are n-1 types monopoles, but this is not true. And this step is shown by Kran and Wambal and Lee, Kim Yong Lee and Piljing Yi. There are actually n types of monopoles, and this difference comes about because in Polyakov, this scalar is adjoint valued, and now the scalar, the thing that replaces the scalar is omega, and this is compact. And in pictures, it is easier. Here you can think two eigenvalues of the scalar, and whenever they fluctuate, and whenever they hit and collide somewhere, the core is a monopole. But when this omega is compact, you can draw a picture like this. You have to identify this with that. You can do like that. This will be a monopole, but you can also do like this. This will be a monopole. In some sense, the eigenvalues here, like this in the center symmetric background, they can collide this way or that way. So there are two types in SU2. There are two types of monopole-instantons. Some people call it dion. It's a wrong terminology. These things do not have electric charge. They only have magnetic charge. So these monopoles have topological charge 1 over n. You can show this. And they have action. They are concrete solutions, and they have action which is 1 over n of the instanton action. It's very important. So the action is 8 pi squared divided by g squared n. And they have a fixed size. Monopole has a fixed size, and the fixed size is mw minus 1. It is inverse of the W boson mass. Okay. And these monopoles, as I said, they are n types. N types. And these are associated with the affine root system. Let me put end nodes of the affine linking diagram of the SUN algebra. These are associated with those. So what do we do with them? Let me see. Actually, let me go back to what I, okay. Oh, okay. Gosh, okay. Let me just describe this abelian duality. Oh, no, I don't have enough time. Let me skip this and I will come back. Okay, so I told you there are these monopoles. These monopoles, oops, sorry, are solutions. They have weight 8 pi square divided by g square. And one thing to notice is that this thing, which is a fractional instanton effect, it is much, 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 much larger than 8 pi square g square. This is the standard BPST instanton. And BPST instanton is not important in this story at all. The important thing is really these fractional instantons. The other important thing, if you consider large n with some 2-Hooft coupling fixed, the usual instantons will be suppressed as exponential of n. But these things, n to the 1, these things, fractional instantons will not be suppressed, exponential minus order n to the 0. So exponential of minus 8 pi square g square n. Physically, what this quantity is, it is really the density of the fractional instantons on the Euclidean setup on R3 cross S1. Okay, so you can, if you take a snapshot of the Euclidean vacuum is filled up with these monopoles with charges plus alpha I, minus alpha j, and some other things, some correlated events that I will come back later. Okay, and this is some sort of magnetic plasma, if you wish, magnetic conductor. And if you put an external magnetic charge to this system, it will exhibit Debye screening and it will exhibit finite correlation length. You will change the 1 over R of the, in the vacuum with this Debye length, with this Yukawa formula. It tells you that you induce a mass gap for the photons. Okay, I wrote a formula. Okay, so this proliferation of the monopoles generate these monopole operators in the action. Okay, so this was the Maxwell term. Proliferation generated these monopole operators, and these monopole operators, as I said, comes in n types. Okay, and this thing generate the Debye screening and generate the mass gap. And you can also show that if we insert an electric charge, I put a slide about it, but I think how much time do I have, Anosh?
Mithat, you have 20 more minutes.
How many?
20 minutes.
20? Oh, it's a lot. It's great. Okay. Actually, then I can tell you one more thing about confinement. Okay.
Okay.
So if you consider, okay, for students, I must tell this. Okay. So for students, let me go back to abelian duality, because it will tell you something interesting about this dual photon field. Okay. And I showed that, this proliferation of the monopoles generate these monopole operators, and they generate these mass gap, Debye, etc. But if you look on 2 plus 1 dimension, you can relate this F mu nu to epsilon mu nu rho del rho sigma. You can relate B electric fields and to this sigma in this way. This is the abelian duality. So using this relation, you can show that actually the circulation of the sigma fields, the vortex of this sigma, if there is a vortex of this sigma, this corresponds to an electrically charged particle. So this is really Gauss's law in terms of sigma fields. So you insert an electric charge. So sigma of theta, the vortex is Q electric times theta. It corresponds to an electric field, which is in 3D 1 over R. And the potential due to it is logarithm R. But because of the magnetic plasma around, you can show that, whenever these monopole-induced terms are there, this configuration, sigma R, if the vortex goes around uniformly like this, this corresponds to electric fields spreading from this test charge uniformly, nicely throughout space. You can show that this costs an energy in the system of order R square. However, you can also show that, the sigma circulation must be 2 pi. You can show that you do not, there's a source here. You do not make any change in the sigma, but here you make a jump that across this, you make a jump such that this circulation is again, I wrote the same thing again, is 2 pi, is 2 pi, okay? Then you can show that this is Q and Q bar pair. You can show that there is linear confinement. This is just slight generalization of the Polyakov. But I will tell you what is very different from Polyakov, okay? So what I said is that there is this dual photon field, and the vortex of the dual photon field is the electric charge, and you can show linear confinement due to that electric charge. So you show mass gap, and linear confinement. But what is difference? Linear confinement. What is different from Polyakov model? The difference from Polyakov model, we have a setup on R3 times S1, which is locally 4D. That means that we have a theta angle. Okay, we have a theta angle. So let me go back to the monopole operator. I wrote the monopole operator here quickly. And I didn't explain everything here. This Sk is the action of the monopole, 8 pi square divided by G square n. This sigma is the dual photon. This alpha K is the magnetic charge of the monopole. And this theta over n is the topological theta angle dependence of the monopole, and it comes with 1 over n. And B is related to the fluctuation of the holonomies. If you are in the non-supersymmetric theory, you can forget about it. It's not very important. In supersymmetric theory and in some other context, it is important, okay? Actually, you can incorporate this theta angle into your effective action, and it will modify this effective action by this theta over n, okay? Then you can calculate mass gap as a function of theta, okay? And here is the result. You calculate the mass gap. Mass gap square is exponential 8 pi square divided by G square n and mw square. You can convert this to strong scale of QCD, of Yang-Mills theory. It is lambda square, lambda ln to the 5/3. And you can show that mass gap is actually a multi-branch function, and each branch has this form, okay? And so it's like each branch has this form, and the mass gap itself is the maximum over these branches. So this is the well-known multi-branch structure of the Yang-Mills vacuum, sometimes called metastable vacua. So, and you see that at least in this context, this mass gap is induced by monopole-instantons, which are fractional instantons. So, and there is a non-trivial theta angle dependence, and this is not present in the Polyakov model. But one thing that may be very interesting to notice is actually the case for n equal 2. Okay, it is cosine, there is a max there, cosine theta plus 2 pi, k can be at either 0 or 1, theta over 2. For n equal 2, if you take theta, this is the usual theta angle pi, so the mass gap vanishes at theta equal pi. But this is actually, so then the coefficient cosine theta over 2, cosine sigma, this is the coefficient of this cosine sigma that vanishes. And at leading order in semi-classics, you know, there is no mass gap. But at second order in semi-classics, there are effects like, oops, I'm sorry. There are effects like this is sk. There are effects like exponential 2sk, cosine 2 sigma. These are something called magnetic pion. So in the fundamental domain of sigma, there are two minima, theta equal pi. So these are cosine 2 sigma magnetic charge 2 instead of magnetic charge 1. So the vacuum is twofold degenerate, but this is nothing but spontaneous CP breaking. So on R4, at theta equal pi, it is believed that CP is broken spontaneously. And this is really semi-classical realization of that effect. You generate a potential, this cosine sigma term dies off because at theta equal pi, its coefficient is 0. There is a second term due to these things called magnetic pions, and they generate a mass gap, but the end effect is vacuum is non-trivial. There are two inequivalent vacua. There are two physically independent vacua to realization of the CP symmetry. Okay. This is one of the main results on R3 cross S1. Okay, very good. I should say that this semi-classical analysis on this, so this is R4, this is R3 cross S1, is only valid whenever this L and lambda is smaller than 1. It is not lambda L less than 1. Because this appearance of N is related to the existence of light W bosons. If you look to the W bosons, mass of the W bosons, it is 2 pi over Ln. So this analysis is reliable in the semi-classical regime, which is continuously connected to the strong coupling regime. I must emphasize that all of the pathologies of the standard instanton analysis on R4 are fixed in this construction. Usually instanton is a moduli. Maybe I should say, let me open a page for students. Where is plus? So on R4, instantons has a, in SUN theory, has a moduli space, and it is, and for SUN, the dimension of this moduli space is 4n. For example, if you take n equal 2, the dimension of this moduli space is 8. So this is at the heart of many problems. So 4 of these 4 of these x sub instanton position. Let me be a little bit. X R4, it is instant where the instanton center is. 4 of these instanton position. One of it is instanton size. It tells you that instanton size can be anything. And 3 of these, let me call this not omega tilde, u of theta is some internal SU2 angle. So the reason that semi-classical analysis is not good on R4 is this, you know, or many, the reason for many pathologies is this instanton size. You know, you start with the assumption that instanton size is much smaller than the separation between instantons, but the size can be anything. So the assumption is meaningless. So what happens on R3 cross S1 is that on R3 cross S1, a monopole K, for the monopole K, dimension of its moduli, monopole K, moduli, there are 4 moduli, 4 of them. And this 4n decomposes as n monopoles times 4. And this 4 is 3 plus 1. It is 3 of them are positioned on R3, and one of them is some U1. Okay, so the size moduli is no longer a problem. It is gone. Okay, so this the pathology of the usual instanton is gone, and the semi-classical analysis is reliable. Okay. Now, actually, I want to show you a very intriguing lattice simulation by Massimo Delia and his collaborators. Okay. So normally, if you consider, for example, topological susceptibility for Yang-Mills theory on maybe on R3 times S1 beta on the normal, the topological susceptibility, if you measure it on the lattice, this is beta. At large beta, let's say it is something dictated by strong scale, then around the deconfinement temperature, it drops to something minuscule. This minuscule thing is, you know, at the phase transition. And here, in this simulation, what Massimo and his friends are doing, they are adding, this is, I think, SU4 theory, and they are adding 2 double trace operator, this trace omega square plus trace omega square, okay? 2 double trace operators. And what happens is that in the absence of these double trace operator, just this green, okay, this green is like the absence of the double trace operator. Oh, this ratio here is the topological susceptibility on R3 times S1 in various deformations, in various deformations on R4 versus R4. You see that whenever you add, this is an insufficient deformation. If this deformation is insufficient, it drops towards 0. But when you add appropriate deformation, this ratio statistically remains 1. It's a very interesting thing. They actually
Mithat, I have a question.
Sure.
So I believe this is on a torus, right? This 6 times 32 power cube lattice, that is a torus.
6 times 32 cube. So this emulates R3 cross S1.
How can you make it R3? I believe they are imposing periodic boundary conditions.
Yeah. But they are using double trace deformations here on this S1. So when it is, if it was 32 to the 4, it would be T4. right?
Right, yeah.
Asymmetric, 32 cube times 6. So it is mimicking R3 cross S1. And on the S1 cycle, they are inserting these deformations and checking how the susceptibility behaves.
Right. How are they introducing R4? The ratio denominator?
Okay. They know the result on R4. These guys did these simulations for a long time, for a living. Yeah, they already know the R4 result, low temperature results.
Right. Okay. Thanks.
Yeah, and when they look to this comparison, instead of this jumping down to 0, this ratio. So this thing, this topological susceptibility essentially remains on this plateau, with these deformations. They also have very nice simulation results for mass gap. And there are some interesting questions there, but maybe I will not go there right away, but maybe I can come back. Now, actually, I want to address a question about something a bit more difficult. It may be difficult for students, I don't know. But there is an important problem in Yang-Mills theory, okay? And this important problem is called IR-Renormalon problem. It is introduced by 't Hooft in 79 in a set of lectures he called Can We Make Sense Out of QCD? And the problem is following. Let me tell you the problem first, okay? So if you look to the Borel plane, there is a singularity here, which is the usual I bar singularity. This is I is the usual BPST instanton, and this singularity is far away, okay? But 't Hooft observed that there are singularities much closer to the origin of the Borel plane. If you study perturbation theory and large momentum region of the perturbation theory, it showed that there are other singularities located at, this is in some normalization, this is located at 2s instanton. These things are located at 4s instanton divided by beta naught, 4s instanton divided by 11/3. And
Hi, Mithat.
Yes.
So time is almost over.
Okay,
so
then
maybe you could finish in 5 or 10 minutes.
Not 10 minutes. 3 minutes is enough.
Okay. All right.
It is nicer to have a discussion than me saying these things.
Okay. All
but
right.
Here is the thing. The problem is that, there are these singularities in perturbation theory if you evaluate it. And 't Hooft called these things IR-Renormalons. And IR-Renormalons are, in some sense, physical. If you have, and this part is UV renormalon, but to address the physics of the theory, you have to consider these Laplace integrals in this direction, okay? So in some sense, IR-Renormalons, the physics of the theory must cure IR-Renormalons. Somebody in the first lecture asked about QED. I can come back to it later. The distinction between Borel plane of QED versus QCD, because I promised I will finish in 3 minutes. So the problem of 't Hooft was that there is no configuration here. If you look at this ratio, it is 12 divided by 11 times n. There is no configurations, known semi-classical configurations here. He had the hope that maybe these things, these IR-Renormalons, may be related to some sort of saddles that we do not yet know. Actually, oddly enough, 't Hooft also introduced 't Hooft flux, and and these things are intimately related. And he also introduced, in that context, fractional instanton. But the problem at the time was that he thought that, at least on R4, there is no such configurations which can give rise to fractional, to these IR-Renormalon singularities. This is one of the last papers of the Hooft concerning QCD relatively. Okay. And if you look to standard perspective emanating from 1970s, I took something from Parisi. He says that in theories, in these renormalizable theories, Borel transform has new singularities which cannot be controlled by using semi-classics. But we did something to the theory. We changed the question. Let's change the question. What happens if we can make the theory semi-classically calculable? What happens to these IR-Renormalons as you do compactification? Now, here is the interesting thing. I told you about monopole, but you can also take monopole, anti-monopole pairs. And you can actually show that this thing contributes to gluon condensates. You know, in the usual story, phenomenologically, it is argued that this IR-Renormalon is related to gluon condensates, trace F square. Okay? And there has to be some ambiguity therein. But now, these M bars, monopole, anti-monopole, two things. Just like our instanton, anti-instanton in QM, you can show that they are twofold ambiguous. Okay. Furthermore, you can show that they calculate to gluon condensates. So at least on our 3 cross S1, these are the leading semi-classical candidates to give rise to configurations like IR-Renormalons. So you do get the factor of n rights. You see the factor of n here is different from here, but after all, this is a semi-classical regime. Because of the adiabatic continuity, you are entitled to expect this n dependence to get correctly, but you are not entitled to get this prefactor correctly. If you get it exactly right, it's a coincidence. But it tells you that these M bar pairs, which are sometimes called neutral bions, are semi-classical realization of IR-Renormalon in this semi-classical regime. Okay, I think I don't want to say anything more here, so I can more or less stop here. So and I can take questions.
Okay, thanks Mithat for a nice lecture. So let's all thank Mithat. Questions?
Mithat, so with this method, can you compare the string tension you get from this Polyakov calculation to string tension of QCD? Is it close?
No, you see, the problem is I can phrase the problem in the context of the mass gap. So when we have the semi-classical theory, we have a small parameter. We have a separation of scales and we have a small parameter. So you see that this analysis is valid provided this thing is less than 1. Okay, so let me put a plus sign here. Okay, so what happens to the mass gap? For example, mass gap arises as mass gap divided by lambda. Let's say L and lambda. This is our small parameter. It grows as L and lambda to the power 5/6. This is L and lambda to power 5/6. But if you make this infinity, this is R4, okay, this point. And this is compactification. And because of this is semi-classical regime, and it is valid as long as this L and lambda less than 1 or much less than 1, okay? But on R4, you have this volume independence result. If you know mass gap, for example, if you have mass gap at some point here, it remains constant because of the volume independence. So the thing that you do not know in this construction I am making is how to connect this semi-classical regime to the volume independence regime as you dial ln lambda. So I can do the same sketch for the string tensions, sigma divided by lambda square, okay? There will be similar sketch here. There will be a semi-classical domain. And if I naively take ln lambda to be order 1, it will go to the strong scale square. But so apart from these, the fact that string tension exists, I do not think that we should draw something numerical. We should not draw something numerical from this construction because it is not entitled, the semi-classical regime is not entitled to agree precisely with R4. It is only entitled to be adiabatically connected to it. But you do get finite string tensions.
That's good. Thank you.
Sure.
The microphones are losing their battery on and off.
Oh, okay. This was David.
More
right?
questions. Weibo.
Have any resurgence calculations or something like that have been done for 4D n equals 2 theories, like super SU2 pure super Yang-Mills? 4D
N
n
equals
equals,
to,
yeah.
the N is supersymmetry?
Yeah, so 8 superchargers.
8 supercharges, okay. I think there is a paper by Honda.
I'm asking because there's if you take the instant-on corrections there, then there's something to compare to because of the Seeberg-Witten formula or localization techniques or Nekrasov partition functions.
Actually, yeah, this is what I think. This is what Honda used. These Nekrasov partition function and comparison with some exact result by using localization technique. But I am not completely familiar with the details of this work. But I know something along these lines exists.
Thank you.
In this theory, it exists. In Chern-Simons theory in 3D, there is a lot of, perturbative data as well as non-perturbative data. So this is 3D. So maybe, yeah, you can look to this paper. Masazumi Honda.
Okay. Thank you.
Sure.
More questions? So participants on Zoom, any questions?
Oops, sorry. Oh, okay.
Seems like there are no